Hello everyone, my name is Varun Tisharaj. Today I'm going to be talking about the relationship between the reaction quotient and Le Chatelier's principle, which is unit 7.10 of AP Chemistry. So what is the relationship between Le Chatelier's principle and the reaction quotient? Well, at equilibrium, the equilibrium constant Kc is equivalent to the reaction quotient Qc. Note that the C indicates we are talking about concentrations. If instead we were talking about partial pressures, then we would use P. Now moving on. When the system is stressed, this equation no longer holds and Kc does not equal Qc. However, according to Le Chatelier's principle, the reaction will shift in such a way that equilibrium is re-established, therefore making the reaction quotient equivalent to the equilibrium constant. Now let's analyze this diagram here. This diagram essentially shows the different effects of when Q is either greater or less than K. If the reaction quotient is less than the equilibrium constant, then the reaction will shift to the right, as there are too many reactants, thus more products will need to be formed. Thus more products are formed, increasing the reaction quotient until it equals the equilibrium constant. At equilibrium, of course, the reaction quotient is equivalent to the equilibrium constant. If the reaction quotient is larger than the equilibrium constant, then the reaction will shift to the left, favoring the reverse reaction, as more reactants must be formed to decrease the reaction quotient until it equals the equilibrium constant. Now let's talk about the various types of stresses and their effects on Le Chatelier's principle and the reaction quotient. So, changes in concentration. The main ways in which concentration is changed in a reaction is by adding or removing a reactant or product, or by adding water to dilute the contents of the reaction. In some cases, you may see that water is not the solvent of the reaction. Instead, ethanol or propanol may be the solvent. In this case, you want to increase or add more of that solvent. Interestingly, concentration does not affect the equilibrium constant. However, it does affect the reaction quotient. The last 2 points at the bottom essentially depict the same thing as the previous diagram, stating that if the reaction quotient is less than the equilibrium constant, then the forward reaction is favored to produce more product and shift the equilibrium to the right, such that the reaction quotient is now equivalent to the equilibrium constant. However, if the reaction quotient is greater than the equilibrium constant, then the reverse reaction is favored to form more reactants to shift the equilibrium to the left, so that the reaction quotient is now equivalent to the equilibrium constant. So now let's explore the effects of changes in temperature. So unlike concentration, changes in temperature affect both the equilibrium constant and the reaction quotient. The table here summarizes the effects. So if the forward reaction is exothermic and the temperature is increased, then the reverse reaction is favored, as products are turned into reactants and both the reaction quotient and equilibrium constant are decreased. Conversely, if the temperature is decreased and the forward reaction is exothermic, then reactants are converted to products because the forward reaction is favored and both the equilibrium constant and the reaction quotient are increased. If the forward reaction is endothermic, then the reactants are converted to products because the forward reaction is favored and both the equilibrium constant and the reaction quotient increase. Conversely, if the temperature is decreased and the forward reaction is endothermic, then the reverse reaction is favored, turning products into reactants, and therefore both the equilibrium constant and the reaction quotient decrease. Note that if the forward reaction is exothermic, then the reverse reaction must be endothermic, and vice versa, which explains why these two boxes say the same thing and these two boxes say the same thing. Now let's move on to an example problem. A reaction between hydrogen gas and iodine gas is described by the following equation. Hydrogen gas reacts with iodine gas to produce 2 moles of hydrogen iodide. At 450 degrees Celsius, the equilibrium constant for the reaction is 50. Our reaction vessel contains the following components. hydrogen gas has a concentration of 0.2, iodine gas has a concentration of 0.1, and hydrogen iodide has a concentration of 1.5. So first we must calculate the reaction quotient, QC, and determine the direction in which the reaction will shift to reach equilibrium. Second, we must explain how the equilibrium position will shift if some of the hydrogen iodide gas is removed from the system, and this must be justified using Le Chatelier's principle. So now let's look at how to solve this problem. So for part A, essentially this involves calculate the formula for the reaction quotient, which for QC in this case will equal the concentration of hydrogen iodide gas squared divided by the concentration of hydrogen gas multiplied by the concentration of iodine gas. Essentially, we know that this is 1.5 divided by 0.2 times 0.1. Plugging this into the calculator, you should get 112.5 as the answer as the value for the reaction quotient. Therefore, QC is greater than KC, indicating that the reverse reaction is favored and the reaction will shift to the left, producing more hydrogen and iodine gas whilst consuming hydrogen iodide. Also note that the hydrogen iodide concentration is squared because the coefficient in the reaction was 2. Okay, for part B, so the effects of removing hydrogen iodide on the equilibrium is that according to Le Chatelier's principle, when a product, which in this case is hydrogen iodide, is removed, the system will shift in a direction that replaces this lost product. Since hydrogen iodide is a product on the right side of the reaction, it will shift to the right side to produce more hydrogen iodide. Therefore, removing hydrogen iodide will shift the equilibrium to the right, increasing the formation of hydrogen iodide and decreasing the concentrations of hydrogen gas and iodine gas. If you wanted any more help or any more resources, you can visit these two links as they offer useful information on Unit 7.10 of AP Chemistry. Thank you.